look what I found. Hi folks, my name is Dan Desjardins. I am the CEO of Distributive, and my background is in computational physics, and today I want to walk people through how they can instantaneously set up computing clusters using computers already around them to do massive amounts of compute without spending a dime on expensive cloud. So check this out. All right, I want to walk you through some code. This was my own code that does some physics simulations and modeling. And inside the main function, we have the compute class and the wallet class. Compute class allows you to distribute computations, and the wallet class allows you to spend compute credits on deploying that job. And you'll see there's only about 5 ingredients in this code that are all you need to distribute big jobs. So the first one is the input set. The input set is an array of anything. The elements can be other arrays, they can be images or frames of a video or CSV files or any data whatsoever. In this case, my array is called parameter sets, and it's a bunch of arrays of sets that will go into a model. The next ingredient is the work function. The work function is arbitrary code that gets executed and applied to each element of the input set. So here my work function I'm calling model, and it takes as an input one of the parameter sets. In here, it's using twoforces.js. This is 600 lines of math code that I wrote, just tucked away neatly behind this package. And out of it, I'm applying the axial force and radial force functions to the parameter set input and returning a result. And the rest is pretty straightforward. Job equals compute.for, parameter sets model. You probably can guess what this does. Normally, a for loop will apply the model to each parameter set one at a time, which will take a considerable amount of computing time. If you add compute dot in front of this for, it becomes a parallel for loop that will map model onto each set of the parameter sets array, and that is the parallel job. Beyond that, job.requires tells the worker agents what packages they need to load and initialize. I can put this job into a private compute group. Right now I'm going to put it into the Dan compute group. Next, give the job some info. So today's date, January 17th, optional description and link. And then events. So here's where I can wire up any event of interest, like when the job's accepted, console, the job ID, and show me that I'm waiting for some results. When I get a result, print it. If there's an error, definitely print it. When the job's finished and the status change, tell me. But it can also launch other jobs or whatever as required. And then finally, job.exec. Let results equals job.execute. And you pay a certain amount of compute credits per slice. You make an offer. The more you put, the faster it'll execute. And which wallet you're going to pay for it with, containing compute credits. So here, I'm paying with my physics wallet. And that's it. This job will automatically deploy, be distributed, and do compute across multiple machines. And when you get those results back, you can plot them or display them or do anything you need. Note that there is no Docker container, image creation, port forwarding, instance management, or data control planes, or infrastructure planes, or anything else. It's literally just input set, work function, job.execute. And the code here to plot these results, ironically, is almost longer than the code to express the parallel job in the first place. So to summarize, input set, arbitrary array of elements, work function, arbitrary code that transforms those elements, compute.for, packages, groups, events, and job execution. Let's run this and see what happens. Now it's asking me for my password, and that's it. Job's deployed. And voila, the job is done using compute all around us. Thank you very much, everyone. Hope you enjoyed the presentation.